In the vast expanse of the cosmos, whispers of the universe's earliest moments echo through time, carrying secrets of its birth and evolution. These whispers, faint yet persistent, are encoded in a form of electromagnetic radiation known as the cosmic microwave background, or CMB. Imagine a time when the universe was young, a seething cauldron of energy and matter. As the universe expanded and cooled, this primordial energy transformed, leaving behind a faint afterglow, a relic of its fiery beginnings. This afterglow, the CMB, permeates all of space, a constant reminder of the universe's dramatic birth. It's a faint hum in the microwave portion of the electromagnetic spectrum, invisible to the naked eye but detectable by sensitive radio telescopes. The discovery of the CMB marked a turning point in our understanding of the universe, providing compelling evidence for the Big Bang Theory and offering a glimpse into the universe's infancy. The CMB is more than just a faint echo. It is a treasure trove of information about the early universe. Like archaeologists carefully excavating ancient ruins, cosmologists study the CMB to piece together the history of the universe. By analyzing its properties, such as its temperature, polarization, and subtle fluctuations, scientists can infer the conditions present in the early universe and trace the evolution of cosmic structures. The discovery of the cosmic microwave background radiation ranks among the most profound achievements in modern cosmology. It provided the first direct evidence for the Big Bang Theory, confirming the idea that the universe originated from an extremely hot, dense state billions of years ago. Before the CMB's discovery, the Big Bang Theory was just one of several competing models attempting to explain the universe's origin and evolution. The CMB's existence had been predicted by cosmologists studying the Big Bang Theory, and its discovery provided crucial support for this model, elevating it to the leading explanation for the universe's beginnings. The CMB's significance extends beyond simply confirming the Big Bang. Its properties, particularly its remarkable uniformity in all directions, provide insights into the fundamental nature of the universe. This uniformity suggests that the early universe was remarkably homogeneous, meaning that matter and energy were distributed evenly throughout space. The slight temperature fluctuations in the CMB, on the order of a few parts per 100,000, reveal the seeds of cosmic structure formation. These tiny variations in density provided the gravitational scaffolding for matter to clump together, eventually forming stars, galaxies, and the large-scale structures we observe in the universe today. To grasp the full significance of the cosmic microwave background radiation, we must first journey back in time to the early 20th century, a period of revolutionary discoveries that transformed our understanding of the universe. In 1929, astronomer Edwin Hubble made a groundbreaking observation that would forever alter our view of the cosmos. By studying the light from distant galaxies, Hubble discovered that they were moving away from us, and the farther away a galaxy was, the faster it was receding. This observation, now known as Hubble's law, implied that the universe was not static and unchanging, as previously believed, but rather expanding, with galaxies moving apart like dots on an inflating balloon. Hubble's discovery of an expanding universe sent shockwaves through the scientific community, challenging long-held assumptions about the nature of the cosmos and paving the way for new theories about its origin. If the universe was expanding, then logically it must have been smaller and denser in the past. Extrapolating this expansion backward in time led to the idea that the universe originated from a single point, an infinitely dense and hot state, a concept that would form the foundation of the Big Bang Theory. Before the advent of modern cosmology, our understanding of the universe was often shaped by philosophical and religious beliefs, with scientific inquiry playing a limited role. However, the 20th century witnessed a dramatic shift as advancements in physics and astronomy provided new tools and observations that challenged traditional views and paved the way for a more empirical understanding of the cosmos. In the early 1900s, Albert Einstein's theory of general relativity revolutionized our understanding of gravity, describing it not as a force acting at a distance, but as a curvature of space-time caused by the presence of mass and energy. Einstein's theory provided a new framework for understanding the large-scale structure of the universe and its evolution, leading to the development of cosmological models that attempted to describe the universe's behavior. One of the first such models, proposed by Einstein himself, described a static and eternal universe, a view that aligned with prevailing scientific thought at the time. However, Einstein's static universe model faced a significant challenge. It was unstable. According to his own equations, gravity should cause a static universe to collapse in on itself. To counteract this gravitational collapse, Einstein introduced a cosmological constant into his equations, a repulsive force that counterbalanced gravity and maintained a static universe. The Cosmic Puzzle, unveiling the mysteries of the universe. In the first half of the 20th century, astronomy and physics were undergoing a period of unprecedented transformation. New technologies, such as larger and more powerful telescopes, allowed astronomers to peer deeper into the cosmos than ever before, revealing a universe far more vast and complex than previously imagined. These observations, coupled with groundbreaking theoretical advancements in physics, particularly Einstein's theory of general relativity, laid the groundwork for a new era of cosmological exploration, one that sought to unravel the mysteries of the universe's origin, evolution, and ultimate fate. The early 20th century was a time of intense intellectual ferment in cosmology. Astronomers and physicists grappled with fundamental questions about the nature of space and time, the distribution of matter and energy in the universe, and the forces that governed its evolution. The prevailing view at the time was that the universe was static and eternal, an idea deeply ingrained in both scientific and philosophical thought. However, this static universe model faced significant challenges as new observations and theoretical insights began to emerge, revealing cracks in the long-held assumptions about the cosmos. The static universe. A prevailing paradigm challenged the idea of a static and eternal universe, often referred to as the steady-state model, held sway for centuries, rooted in both philosophical and religious beliefs. This model proposed that the universe had always existed in its present form, unchanging and infinite in both space and time. The static universe model found support in the apparent lack of observational evidence for any large-scale motions of galaxies. Without the means to accurately measure the velocities of distant objects, astronomers had little reason to doubt the prevailing view of a cosmos frozen in time. However, this seemingly comfortable paradigm began to crumble in the face of new theoretical developments and observational breakthroughs. Einstein's theory of general relativity, published in 1915, provided a new framework for understanding gravity, one that challenged the Newtonian view of a force acting at a distance. Einstein's theory described gravity as a curvature of space-time caused by the presence of mass and energy. This revolutionary concept had profound implications for our understanding of the universe on its largest scales. The birth of modern cosmology, Hubble's expanding universe. In 1929, Edwin Hubble made an observation that would revolutionize our understanding of the universe and usher in the era of modern cosmology. By studying the light from distant galaxies, Hubble discovered a remarkable pattern. The galaxies were moving away from us, and the farther away a galaxy was, the faster it was receding. Hubble's discovery, now known as Hubble's law, provided the first compelling evidence that the universe was not static and eternal, but rather expanding, with galaxies moving apart like dots on an inflating balloon. This groundbreaking observation sent shockwaves through the scientific community, challenging the long-held belief in a static universe and forcing cosmologists to reconsider their fundamental assumptions about the nature of the cosmos. Hubble's discovery was a watershed moment in cosmology, marking a paradigm shift from a static to a dynamic universe, one characterized by constant motion and evolution. The implications of Hubble's expanding universe were profound. If the universe was expanding, then logically it must have been smaller and denser in the past. This realization provided the first hints of a universe with a finite age and a dramatic beginning, paving the way for the development of the Big Bang Theory. Section 4. The Big Bang Theory, a bold idea, takes shape. The idea that the universe originated from a single point, an infinitely dense and hot state, emerged gradually in the years following Hubble's discovery of an expanding universe. This concept, which would eventually become known as the Big Bang Theory, challenged the prevailing view of a static and eternal cosmos, proposing instead a universe with a finite age and a dramatic beginning. The term Big Bang was actually coined by physicist Fred Hoyle, a staunch critic of the theory, as a way to ridicule its seemingly outlandish implications. However, the name stuck, and the Big Bang Theory, despite initial skepticism, gradually gained traction as a compelling explanation for the observed expansion of the universe and other cosmological phenomena. The Big Bang Theory postulates that the universe originated approximately 13.8 billion years ago from an extremely hot, dense state. In the first fraction of a second after the Big Bang, the universe underwent a period of rapid expansion and cooling, with energy transforming into matter and antimatter, followed by the formation of the first elementary particles. Section 1. Holmdel Horn Antenna, a window to the cosmos. Nestled in the tranquil countryside of Holmdel Township, New Jersey, a large horn-shaped antenna stood as a silent sentinel, poised to unlock secrets of the cosmos. This unassuming structure, known as the Holmdel Horn Antenna, was originally designed for satellite communication, but fate had other plans for this technological marvel. It would become the instrument of one of the most profound discoveries in the history of cosmology: the accidental detection of the cosmic microwave background radiation. The Holmdel Horn Antenna, built by Bell Telephone Laboratories in 1959, was a marvel of engineering for its time. Its large horn-shaped design, resembling a giant ear trumpet pointed towards the heavens, made it exceptionally sensitive to faint radio waves emanating from the depths of space. This remarkable sensitivity, coupled with its ability to minimize interference from terrestrial sources, made it an ideal instrument for exploring the radio universe, a realm of celestial objects and phenomena that emit radio waves invisible to the naked eye, but detectable by sensitive radio telescopes. Section 2. The persistent hum, an unexpected signal. In 1964, two young radio astronomers, Arno Penzias and Robert Wilson, arrived at Bell Laboratories to begin work on the Holmdel Horn Antenna. Their initial goal was to use the antenna for radio astronomy observations, studying distant galaxies and other celestial objects that emit radio waves. However, their plans took an unexpected turn when they encountered a mysterious signal that would forever alter the course of their careers and revolutionize our understanding of the universe.
As we began our observations, we noticed a faint, persistent hum in the antenna's data. a constant background noise that seemed to permeate all of space.
This unexpected signal, initially dismissed as interference from terrestrial sources or instrument noise, proved to be remarkably stubborn, defying all attempts to eliminate it. They meticulously calibrated their instruments, checking and rechecking their data for any signs of error. They even resorted to removing a family of pigeons that had taken up residence inside the antenna's horn, meticulously cleaning out the accumulated droppings in hopes of eliminating the pesky noise. Despite their best efforts, the mysterious signal persisted, a constant hum that seemed to emanate from the cosmos itself. Determined to identify the source of the mysterious signal, we embarked on a systematic process of elimination, meticulously ruling out every conceivable source of terrestrial interference.
We conducted our observations at different times of day and night, reasoning that any terrestrial interference would likely fluctuate with human activity or atmospheric conditions. They pointed the antenna in different directions, hoping to find variations in the signal strength that might betray a local origin. Despite our exhaustive efforts, the signal remained constant, its strength unwavering regardless of the antenna's orientation, the time of day, or any other environmental factors we could identify. They even consulted with experts in radio engineering and atmospheric science, seeking any plausible explanation for the persistent hum that plagued their data.
The signal's persistence and its uniform presence across the sky suggested that it did not originate from Earth or its atmosphere. It seemed to be coming from beyond our solar system, perhaps even from the farthest reaches of the cosmos. As Penzias and Wilson grappled with the enigma of the persistent hum, a group of physicists at nearby Princeton University, led by Robert Dicker, were pursuing a seemingly unrelated line of research.
Dicker and his team were developing a theory that predicted the existence of a faint afterglow from the Big Bang, a relic of the universe's hot, dense beginnings.
This afterglow, they reasoned, would have cooled as the universe expanded, shifting its wavelength from the visible to the microwave portion of the electromagnetic spectrum.
Dicker's team was in the process of building a specialized antenna to search for this predicted cosmic afterglow when fate intervened, bringing them into contact with us.
In a serendipitous encounter, a colleague mentioned Penzias and Wilson's struggles with the persistent hum to Dicker, piquing his curiosity.
Dicker immediately recognized the potential significance of our findings, realizing that the mysterious signal we detected could be the very cosmic afterglow his team had been seeking.
Armed with the theoretical framework provided by Dicker's work, Penzias and Wilson began to see their unexpected signal in a new light.
The persistent hum, once a source of frustration, now held the potential to unlock profound secrets about the universe's origins.
They carefully compared their data to the predictions of Dicker's theory, looking for any discrepancies that might cast doubt on the cosmic origin of the signal.
To our astonishment, the characteristics of the signal, particularly its temperature and its uniform presence across the sky, aligned remarkably well with the predicted properties of the cosmic afterglow.
The signal's temperature, measured at approximately 3 degrees Kelvin above absolute zero, indicated that it originated from a time when the universe was much hotter and denser than it is today.
Its uniform distribution across the sky suggested that it permeated all of space, a relic of a time when the universe was in a much more homogeneous state.
While Penzias and Wilson were grappling with their unexpected discovery at Bell Labs, a team of physicists at Princeton University, led by Robert Dicker, was hot on the trail of the same cosmic phenomenon. The Dicker Group, which included Jim Peebles, David Roll, and David Wilkinson, had independently predicted the existence of the cosmic microwave background radiation as a faint afterglow of the Big Bang. Peebles, a brilliant theoretical physicist, had been exploring the implications of a hot, dense early universe, building upon the work of George Gamow and his collaborators. Gamow had laid the groundwork for the Big Bang theory in the 1940s, proposing that the universe originated from a primordial fireball. Peebles took Gamow's ideas a step further, developing detailed calculations that predicted the existence and properties of the CMB radiation. Roll and Wilkinson, skilled experimentalists, were tasked with building a sensitive microwave receiver to search for this elusive cosmic signal. They designed and constructed a Dicker radiometer, a specialized instrument capable of detecting faint microwave radiation against the background noise of the sky.
The realization that two independent groups, one focused on observations and the other on theory, had converged on the same profound discovery sent shockwaves through the scientific community.
Penzias and Wilson's serendipitous detection of the cosmic microwave background radiation, coupled with the Dicker Group's theoretical prediction and ongoing experimental efforts, provided compelling evidence for the Big Bang theory and forever changed our understanding of the universe's origins.
The scientific community, initially skeptical of the Big Bang theory, which challenged the long-held belief in a static and eternal universe, began to embrace this revolutionary idea as the most plausible explanation for the observed expansion of the universe and the existence of the CMB radiation.
The independent confirmation of the CMB radiation by two separate groups, each with its own strengths and expertise, solidified the discovery's significance and silenced many of the Big Bang theory's critics. This convergence of theory and observation marked a pivotal moment in the history of cosmology, ushering in a new era of scientific exploration focused on understanding the universe's earliest moments and its evolution over billions of years.
The profound impact of Penzias and Wilson's discovery of the cosmic microwave background radiation on our understanding of the universe did not go unnoticed.
In 1978, they were awarded the Nobel Prize in Physics, a testament to the transformative nature of their findings. The Nobel Committee recognized their meticulous observations, their persistence in pursuing an unexpected signal, and their open-mindedness in considering its potential cosmological significance. The award citation stated that Penzias and Wilson's discovery has made it possible to obtain a much more complete view of the early stages of development of the universe and marked a step in the direction of going back to the beginning of time.
The Nobel Prize not only honored Penzias and Wilson's groundbreaking work, but also highlighted the importance of serendipity and collaboration in scientific discovery. Their accidental detection of the CMB radiation, coupled with their interactions with the Dicker Group at Princeton, demonstrated the interconnectedness of scientific inquiry and the often unpredictable path to groundbreaking discoveries.
Section 9, a paradigm shift. The Big Bang theory solidified. The discovery of the cosmic microwave background radiation marked a turning point in cosmology, providing the most compelling evidence to date for the Big Bang theory and solidifying its status as the leading explanation for the universe's origins. Before the CMB's detection, the Big Bang theory faced significant challenges from alternative models, such as the steady-state theory, which proposed a universe that was eternal and unchanging. The CMB's existence, predicted by Big Bang cosmologists, dealt a fatal blow to the steady-state theory and other competing models, which could not account for this faint afterglow from a hot, dense early universe. The CMB's properties, such as its temperature and its uniform distribution across the sky, provided strong support for the Big Bang theory's key predictions, convincing many skeptics and ushering in a new era of cosmological research focused on understanding the universe's early evolution. Section 10. The universe's baby picture, a glimpse into the past. The cosmic microwave background radiation is often referred to as the universe's baby picture because it provides a snapshot of the cosmos as it existed just 380,000 years after the Big Bang. Before this time, the universe was a hot, dense soup of charged particles, opaque to light. As the universe expanded and cooled, these charged particles combined to form neutral atoms, primarily hydrogen, allowing light to travel freely for the first time. This cosmic dawn marked the moment when the universe became transparent, releasing the light that we now observe as the cosmic microwave background radiation. By studying the CMB's properties, such as its temperature fluctuations, cosmologists can probe the conditions present in the early universe and gain insights into the processes that led to the formation of stars, galaxies, and the large-scale structures we observe today. Deciphering the early universe. The discovery of the cosmic microwave background radiation in 1965 marked a pivotal moment in our understanding of the universe's history. Like a cosmic Rosetta Stone, the CMB carries secrets of a young, hot, and rapidly expanding universe. Analyzing its properties, cosmologists confirmed key predictions of the Big Bang theory. The CMB's discovery transformed cosmology into an observational science. Before its detection, the Big Bang theory lacked direct observational support. The CMB confirmed the Big Bang's picture of a universe born from a fiery cataclysm. The CMB's faint glow represents the oldest light we can observe. This baby picture of the universe reveals a cosmos remarkably different from today. The echo of creation. How the CMB supports the Big Bang. The Big Bang theory suggests the universe began from an extremely hot, dense state about 13.8 billion years ago. The early universe rapidly expanded and cooled, forming the first elementary particles. A key prediction is the existence of a faint afterglow of radiation, a relic of the universe's hot beginnings. The discovery of the cosmic microwave background provided direct evidence for this cosmic afterglow. Section 3. The temperature puzzle, a universe bathed in afterglow. One of the most compelling pieces of evidence supporting the Big Bang theory is the remarkably uniform temperature of the cosmic microwave background, or CMB radiation. Measurements from space-based telescopes such as NASA's Cosmic Background Explorer, or COBE, and Wilkinson Microwave Anisotropy Probe, or WMAP, have revealed that the CMB has an average temperature of approximately 2.725 Kelvin, which is minus 455 degrees Fahrenheit, with only tiny variations from this average across the entire sky. This near-perfect uniformity in temperature is precisely what the Big Bang theory predicts for a universe that originated from a hot, dense state. In the early universe, before the CMB was released, matter and radiation were tightly coupled, constantly interacting and exchanging energy. This constant interaction ensured that the temperature remained remarkably uniform throughout the early universe. As the universe expanded and cooled, the energy density of radiation decreased faster than the energy density of matter, eventually leading to a decoupling of matter and radiation. At this point, approximately 380,000 years after the Big Bang, the universe became transparent, allowing the CMB to travel freely through space. The CMB's remarkably uniform temperature observed today reflects this early epoch of thermal equilibrium in the universe's history, providing strong support for the Big Bang model. Section 4. The uniformity enigma: seeds of structure in a smooth cosmos. While the near-perfect uniformity of the cosmic microwave background, or CMB, radiation provides compelling evidence for the Big Bang theory, it also presents a significant puzzle. How did a universe so smooth and homogeneous in its early stages evolve into the complex, structured cosmos we observe today, filled with galaxies, galaxy clusters, and vast cosmic voids? The answer to this enigma lies in the subtle temperature fluctuations within the CMB, tiny variations from the average temperature that provide crucial clues to the seeds of cosmic structure formation. These temperature fluctuations, on the order of a few parts per 100,000, represent slight variations in the density of the early universe. Regions with slightly higher densities had slightly stronger gravitational pull, attracting matter from their surroundings and gradually growing over time. These density variations, amplified by gravity over billions of years, eventually gave rise to the large-scale structures we observe in the universe today. The pattern and distribution of these temperature fluctuations in the CMB contain a wealth of information about the universe's composition, its geometry, and the physical processes that governed its early evolution. By carefully analyzing these fluctuations, cosmologists can test their models of the early universe and constrain the properties of its constituents, such as dark matter and dark energy. Section 5, From Soup to Structure. The growth of cosmic inhomogeneities. The subtle temperature fluctuations observed in the cosmic microwave background radiation provide a glimpse into the early stages of cosmic structure formation, revealing a universe on the cusp of transitioning from a smooth, homogeneous soup of particles to a complex web of galaxies, galaxy clusters, and cosmic voids. These tiny variations in temperature, representing slight overdensities and underdensities in the matter distribution of the early universe, acted as seeds for gravitational instability, gradually amplifying over billions of years to form the large-scale structures we observe today. The growth of these cosmic inhomogeneities was driven by a delicate interplay between gravity, which acted to pull matter together, and the expansion of the universe, which tried to smooth out these density variations. In the early universe, when the density of matter was high, gravity dominated, allowing overdense regions to collapse and form bound structures. As the universe expanded and the density of matter decreased, the expansion rate began to play a more significant role, slowing down the growth of structures. The competition between gravity and expansion determined the rate at which cosmic structures formed and evolved. Regions with larger initial overdensities collapsed earlier and formed more massive structures, while regions with smaller overdensities took longer to collapse and formed less massive structures. Section 6. The fingerprint of inflation, echoes of a rapid expansion. While the Big Bang theory successfully explains the expansion of the universe, the existence of the cosmic microwave background radiation, and the formation of cosmic structures, it faces certain challenges when trying to account for some of the observed properties of the universe, such as its remarkable uniformity on large scales and the specific pattern of temperature fluctuations in the CMB. To address these challenges, cosmologists have proposed an extension to the Big Bang theory called inflation, a period of exponential expansion that occurred in the first fraction of a second after the Big Bang. According to the theory of inflation, the universe underwent a brief but dramatic period of exponential expansion, growing from a size smaller than an atom to a size larger than a grapefruit in a tiny fraction of a second. This rapid expansion would have smoothed out any initial inhomogeneities in the universe, explaining the observed uniformity of the CMB temperature on large scales. Furthermore, inflation predicts that quantum fluctuations in the early universe would have been stretched to cosmological scales during this rapid expansion, leaving an imprint on the CMB in the form of a specific pattern of temperature fluctuations. The observed pattern of temperature fluctuations in the CMB, with its characteristic peaks and troughs, provides strong support for the theory of inflation. Section 7. The Matter-Energy Recipe, Probing the Cosmic Inventory. The cosmic microwave background radiation provides a window into the universe's composition, allowing cosmologists to determine the relative abundances of its constituents, normal matter, dark matter, and dark energy, by carefully analyzing the pattern of temperature fluctuations in the CMB. Cosmologists can infer the universe's matter and energy budget, providing insights into the nature of these mysterious components that make up the vast majority of the cosmos. Normal matter, the stuff that makes up stars, planets, and everything we can see, accounts for only about 5% of the universe's total energy density. Dark matter, a mysterious form of matter that does not interact with light, makes up about 27% of the universe's energy density. Its presence is inferred from its gravitational effects on visible matter, such as the rotation of galaxies and the gravitational lensing of light. The remaining 68% of the universe's energy density is attributed to dark energy, a mysterious force that is causing the expansion of the universe to accelerate. The existence of dark energy was first inferred from observations of distant supernovae, which indicated that the expansion of the universe was speeding up, not slowing down as expected. Section 8. Dark matter's gravitational hand, shaping the cosmic web. Dark matter, despite its elusive nature, plays a crucial role in the formation and evolution of cosmic structures. Its gravitational influence, though invisible to our eyes, is evident in the large-scale distribution of galaxies and the intricate cosmic web of filaments and voids that make up the universe's largest structures. Dark matter's gravitational pull acted as a scaffolding in the early universe, attracting normal matter and forming the seeds for galaxies and galaxy clusters. Without dark matter, the universe would look vastly different. Simulations of cosmic structure formation without dark matter fail to reproduce the observed distribution of galaxies, producing a universe that is too smooth and homogeneous. Dark matter's presence is essential to explain the clumpiness of matter on large scales and the formation of the intricate cosmic web. Dark matter's gravitational influence is also evident in the rotation of galaxies. Observations of spiral galaxies, such as our own Milky Way, reveal that stars in the outer regions of these galaxies rotate much faster than expected based on the visible matter alone. This discrepancy between the observed rotation speeds and the predicted speeds based on visible matter provides strong evidence for the presence of a halo of invisible dark matter surrounding each galaxy, extending far beyond the visible disk of stars and gas. Section 9. The elusive dark energy accelerating the cosmic expansion. In the late 1990s, observations of distant supernovae used as cosmic distance markers revealed a startling discovery. The expansion of the universe was not slowing down as expected due to gravity, but was instead accelerating. This unexpected finding, which earned the 2011 Nobel Prize in Physics, implied the existence of a mysterious force counteracting gravity on cosmic scales, pushing galaxies apart at an ever-increasing rate. This enigmatic force, dubbed dark energy, remains one of the most profound mysteries in modern cosmology. Dark energy is thought to permeate all of space, acting as a form of anti-gravity that drives the accelerated expansion of the universe. Its nature and origin remain unknown, but It is thought to account for approximately 68% of the universe's total energy density. The cosmic microwave background, CMB radiation, provides independent evidence for the existence of dark energy. By analyzing the pattern of temperature fluctuations in the CMB, cosmologists can infer the universe's geometry and its matter and energy content. These analyses indicate that the universe's geometry is close to flat, meaning that it obeys the rules of Euclidean geometry on large scales. This flatness, combined with the observed acceleration of the universe's expansion, implies the existence of a component of energy with negative pressure, precisely the property expected for dark energy. Section 10. A universe, fine-tuned. The remarkable balance of cosmology. The cosmic microwave background CMB radiation reveals a universe that is remarkably fine-tuned for the emergence of complex structures, such as galaxies, stars, and planets, ultimately leading to the conditions necessary for life as we know it. The precise values of the fundamental constants of nature, the relative abundances of different forms of matter and energy, and the initial conditions of the universe all appear to be delicately balanced to allow for the development of a universe capable of supporting life. For example, if the expansion rate of the universe was slightly faster, galaxies would not have had enough time to form before being pulled apart by the expansion. If the expansion rate was slightly slower, the universe would have collapsed back in on itself before stars and galaxies could form. Similarly, the relative abundances of dark matter and dark energy play a crucial role in the formation of cosmic structures. Too much dark matter would have led to a universe dominated by black holes, while too little would have resulted in a universe too diffuse to form galaxies. The observed balance between these components suggests a universe that is remarkably fine-tuned for the emergence of complexity and life. The cosmic microwave background radiation, a faint afterglow of the Big Bang, reveals a cosmos vastly different from today. Like a tapestry woven from primordial light, the CMB carries a wealth of information about the universe's infancy. Imagine a time when the universe was a seething cauldron of particles and radiation, expanding and cooling. Approximately 380,000 years after the Big Bang, the universe underwent recombination, forming neutral hydrogen atoms. This cosmic dawn marked the universe becoming transparent, releasing the light we now observe as the CMB. While the cosmic microwave background radiation appears remarkably uniform at first glance, with an average temperature of approximately 2.725 Kelvin, closer inspection reveals subtle temperature fluctuations, tiny variations from this average that hold the key to understanding the formation of cosmic structures. These temperature fluctuations, on the order of a few parts per 100,000, represent slight variations in the density of the early universe, the seeds from which galaxies, galaxy clusters, and the cosmic web would eventually grow. Imagine the early universe as a vast, smooth ocean, with these density variations acting as tiny ripples on its surface. Over time, gravity amplified these ripples, pulling matter together into increasingly dense regions. These overdense regions, representing the seeds of future galaxies and galaxy clusters, grew denser and hotter as they attracted more matter from their surroundings, eventually collapsing under their own gravity to form the bound structures we observe today. The pattern of these temperature fluctuations in the CMB, often visualized as a map of hot and cold spots across the sky, is not random. Instead, it reflects the physical processes that governed the early universe, such as the interplay between gravity, pressure, and the expansion of space itself. By carefully analyzing this pattern, cosmologists can learn about the universe's composition, its geometry, and the physics that shaped its early evolution. To extract meaningful information from the subtle temperature fluctuations in the cosmic microwave background radiation, cosmologists use a mathematical tool known as the power spectrum. The power spectrum quantifies the strength of temperature variations at different angular scales on the sky, providing a compact representation of the CMB's statistical properties. Imagine scanning the CMB map with circles of different sizes, measuring the average temperature difference between points separated by the circle's diameter. The power spectrum plots these average temperature differences as a function of the circle's angular size, revealing how the strength of temperature fluctuations varies with scale. The resulting graph, the power spectrum, exhibits a series of peaks and troughs, each corresponding to a specific physical scale in the early universe. The positions and heights of these peaks and troughs contain a wealth of information about the universe's composition, its geometry, and the physics that governed its early evolution. By comparing the observed power spectrum to theoretical predictions from different cosmological models, cosmologists can constrain the values of key cosmological parameters, such as the universe's age, its curvature, and the relative abundances of its constituents, such as dark matter and dark energy. Section 4. The acoustic peaks, echoes of the early universe. The acoustic peaks in the cosmic microwave background, radiation's power spectrum, offer a window into early universe physics. These peaks, like musical resonances, reflect gravity, pressure, and space expansion after the Big Bang. The early universe was a hot, dense plasma of protons, electrons, and photons. Small density variations created regions of higher and lower pressure. Gravity and pressure interactions caused oscillations or sound waves in the plasma. These sound waves left temperature fluctuations in the cosmic microwave background. Section 5. The Baryon acoustic oscillations, a cosmic yardstick. The acoustic peaks observed in the cosmic microwave background radiation's power spectrum are not the only evidence for sound waves propagating through the early universe. Another telltale signature of these primordial oscillations, known as baryon acoustic oscillations, can be observed in the distribution of galaxies in the late universe, providing a powerful tool for measuring cosmic distances and probing the nature of dark energy. Imagine the sound waves propagating through the early universe as ripples spreading outward from a stone dropped into a pond. These ripples, carrying information about the initial conditions of the universe, left their mark on the distribution of matter, creating a characteristic clustering pattern that persisted even as the universe expanded and evolved. This clustering pattern, with a characteristic scale of approximately 500 million light-years, acts as a standard ruler that can be used to measure cosmic distances. By observing the distribution of galaxies at different redshifts, which correspond to different epochs in the universe's history, cosmologists can measure how this characteristic scale has evolved over time, providing insights into the expansion history of the universe and the nature of dark energy. Section 6. The polarization of the cosmic microwave background, probing the first moments. While the temperature fluctuations in the cosmic microwave background radiation provide a wealth of information about the early universe, the cosmic microwave background's polarization, a subtle but important property of light, offers an even more pristine view of the universe's infancy, potentially revealing secrets about the universe's first moments after the Big Bang. Light is an electromagnetic wave, with electric and magnetic fields oscillating perpendicular to each other and to the direction of propagation. Polarization refers to the orientation of these oscillating electric fields. Light can be unpolarized, with the electric fields oscillating in random directions, or polarized, with the electric fields oscillating in a preferred direction. the cosmic microwave background radiation is polarized, with a faint but measurable pattern of polarization across the sky. This polarization pattern was imprinted on the cosmic microwave background during the epoch of recombination, when photons scattered off electrons for the last time before the universe became transparent. The polarization of the cosmic microwave background provides a unique window into the physics of the early universe, potentially revealing signatures of gravitational waves generated during inflation, a hypothesized period of exponential expansion that occurred in the first fraction of a second after the Big Bang. Section 7. The Epoch of Recombination, when light broke free. Approximately 380,000 years after the Big Bang, the universe underwent a profound transformation, transitioning from a hot, dense plasma of charged particles to a cooler, more neutral gas, allowing light to travel freely for the first time. This epoch, known as recombination, marked a pivotal moment in the universe's history, releasing the light that we now observe as the cosmic microwave background, CMB radiation. Before recombination, the universe was opaque to light. Photons, the particles that carry electromagnetic radiation, were constantly scattering off free electrons, preventing them from traveling long distances. The universe was like a dense fog, with light constantly bouncing off particles unable to escape. As the universe expanded and cooled, the energy of photons decreased, and eventually they no longer had enough energy to keep electrons stripped from protons. Protons and electrons combined to form neutral hydrogen atoms, a process known as recombination. With fewer free electrons to scatter off, photons were finally free to travel unimpeded through the universe, creating a surface of last scattering that we observe as the CMB. Section 8. The Dark Ages, a universe in transition. The epoch of recombination, which released the cosmic microwave background, CMB radiation, marked the beginning of a period in the universe's history known as the Dark Ages. During this era, which lasted for hundreds of millions of years, the universe was a relatively quiet and uneventful place, devoid of stars and galaxies, its darkness illuminated only by the faint afterglow of the Big Bang. With the formation of neutral hydrogen atoms, the universe became transparent to light, but it also became shrouded in darkness. The CMB photons, stretched and cooled by the universe's expansion, were no longer energetic enough to ionize hydrogen atoms, meaning that the universe was filled with a neutral hydrogen gas that absorbed ultraviolet radiation, preventing the formation of stars. The Dark Ages were a crucial period of transition in the universe's history. During this time, the subtle density variations imprinted on the CMB by acoustic oscillations in the early universe gradually grew under the influence of gravity, setting the stage for the formation of the first stars and galaxies. These first stars, forming within collapsing clouds of hydrogen and helium, would eventually flood the universe with ultraviolet radiation, ending the Dark Ages and ushering in a new era of cosmic dawn. Section 9. The Cosmic Dawn, the First Stars Ignite. After hundreds of millions of years of darkness, the universe erupted with light as the first stars ignited, marking the end of the Dark Ages and the beginning of the cosmic dawn. These first stars, formed from the primordial hydrogen and helium that filled the early universe, were vastly different from the stars we observe today, playing a crucial role in shaping the universe as we know it. The first stars, known as population 3 stars, were likely much more massive and luminous than typical stars today, emitting intense ultraviolet radiation that gradually ionized the surrounding neutral hydrogen gas, a process known as reionization. This reionization of the universe transformed it from a neutral gas back into a plasma, allowing light to travel freely once again. The cosmic dawn marked a turning point in the universe's evolution. The intense radiation from the first stars not only ionized the surrounding gas, but also provided the energy necessary for the formation of heavier elements within their cores. These heavier elements, forged in the nuclear furnaces of the first stars, would eventually be scattered throughout the universe by supernova explosions, enriching the interstellar medium and providing the building blocks for future generations of stars and galaxies. The cosmic microwave background radiation has provided a treasure trove of information about the early universe, confirming key predictions of the Big Bang theory and revealing a cosmos shaped by a delicate interplay of gravity, pressure, and the expansion of space itself. However, the CMB still holds many secrets, and future observations and theoretical advancements promise to unlock even more profound insights into the nature of the universe. One of the most exciting frontiers in CMB research is the search for primordial gravitational waves, ripples in space-time generated during inflation, a hypothesized period of exponential expansion that occurred in the first fraction of a second after the Big Bang. These gravitational waves, if detected, would provide a unique window into the universe's earliest moments, potentially revealing the energy scale of inflation and the physics that governed the universe at its birth. Another promising avenue of research is the study of CMB spectral distortions, tiny deviations from the CMB's blackbody spectrum that could reveal the presence of exotic particles or interactions in the early universe. By carefully measuring the CMB's spectrum with unprecedented precision, cosmologists hope to uncover new physics beyond the standard model of particle physics. The discovery of the cosmic microwave background in 1965 transformed cosmology into a precision science. The CMB provided a tangible link to the early universe, allowing cosmologists to test their theories with unprecedented accuracy. Its near-perfect blackbody spectrum at 2.725 Kelvin supported the Big Bang theory. The CMB's uniformity and tiny temperature variations pointed to a homogeneous early universe. The CMB's role in probing early homogeneity and structure formation made it a cornerstone of modern cosmology. The discovery of the cosmic microwave background radiation provided compelling evidence for the Big Bang theory. With the CMB, cosmologists could measure key cosmological parameters with unprecedented accuracy. Space missions like NASA's Cosmic Background Explorer and the Planck satellite revolutionized our understanding of the CMB. These missions determined the universe's age to be approximately 13.8 billion years. They confirmed the universe's geometry is remarkably close to flat. Section 3. Dark Matter and Dark Energy, unveiling the universe's hidden components. The CMB radiation reveals dark matter and dark energy, the universe's most enigmatic components. Dark matter, undetectable by light, is inferred through gravitational effects. Dark energy drives the universe's accelerated expansion. CMB fluctuations help infer the universe's matter and energy content. The universe's energy budget is dominated by dark matter and dark energy. Section 4. Cosmic inflation, echoes of a rapid expansion. The cosmic microwave background radiation has provided compelling evidence for cosmic inflation. Inflation explains the universe's remarkable uniformity and the specific pattern of temperature fluctuations in the CMB. The universe grew from smaller than an atom to larger than a grapefruit in a tiny fraction of a second. The This rapid expansion smoothed out initial inhomogeneities, explaining the CMB's uniformity. Inflation stretched quantum fluctuations to cosmological scales, leaving an imprint on the CMB. Section 5. The Cosmic Symphony, connecting the CMB to the large-scale structure. The cosmic microwave background radiation provides a snapshot of the universe as it existed just 380,000 years after the Big Bang, while observations of galaxies and galaxy clusters reveal the universe's structure as it exists today, billions of years later. Remarkably, these two vastly different epochs in the universe's history are intimately connected, with the seeds of the large-scale structure we observe today imprinted on the subtle temperature fluctuations in the CMB. The acoustic oscillations that propagated through the early universe, leaving their mark on the CMB's power spectrum, also influenced the distribution of matter on large scales. These oscillations created a characteristic clustering pattern in the matter distribution, with overdense regions more likely to form galaxies and galaxy clusters, while underdense regions evolved into cosmic voids. This connection between the CMB and the large-scale structure allows cosmologists to test their models of structure formation and constrain cosmological parameters using both early and late-time observations. By comparing the statistical properties of the CMB's temperature fluctuations to the distribution of galaxies in the late universe, cosmologists can verify that their models accurately describe the evolution of cosmic structure over billions of years. This interplay between early and late-time observations highlights the remarkable coherence of the universe's evolution from its infancy to the present day. The enduring legacy of the CMB. The discovery of the cosmic microwave background radiation reshaped our understanding of the universe. This faint afterglow of the Big Bang illuminates the universe's earliest moments. It has ushered in a new era of precision cosmology, refining our models of the universe's evolution. The CMB revealed a universe dominated by dark matter and dark energy. It continues to pose profound questions about the universe's origins and fate. Section 2, From Speculation to Precision, the Transformation of Cosmology. The discovery of the cosmic microwave background radiation marked a turning point in cosmology, transforming it from speculation to precision science. The CMB provided a tangible link to the early universe, allowing cosmologists to test their theories with unprecedented accuracy. The CMB's impact on cosmology can be likened to the transformative effect of the telescope on astronomy. Its properties have provided stringent tests for cosmological models, solidifying the Big Bang theory. Mysteries yet to be solved. Despite insights from the cosmic microwave background, the universe holds many mysteries. The CMB raises profound questions, challenging our understanding of fundamental physics. Dark matter and dark energy remain elusive, defying explanation within the standard model. The CMB's temperature fluctuations support the theory of inflation, yet details remain mysterious. These questions drive research, pushing the boundaries of our theoretical models and observational capabilities.